Alhamdulillahi Rabbil Alameen, As-salatu was-salamu ala Rasulil Kareem wa ala alihi wa sahbihi ajma'in, amma ba'd. A'udhu billahi minash shaitanir rajeem, bismillahir rahmanir rahim. Assalamu alaikum everyone. Thank you for being here today to explore the wonders of the universe. हमेशा से इंसान को आसमान की बुलंदियों ने, खला की वसअतों ने और चमकते सितारों ने अपनी तरफ राग़िब किया है। उसके दिल में बेशुमार सवालात पैदा किए हैं। इसी तजस्सुस में एस्ट्रोनॉमी का जन्म हुआ। आज आपके कुछ सवालों के जवाबात के साथ हम हाजिर हैं। To commence our cosmic journey, I invite our shining stars on stage. I invite the esteemed Dean School of Sciences, Professor Salman Ahmed Khan. You'll be glad to know he's among the 2% scientists of the world. Next, I invite the heart that pumps blood to physics section, the heart and head of the section, our very own Professor Aleem Basha. Now I call upon Dr. Priya Hassan, the coordinator of this event. No, I'm just saying, आप यहीं बैठ, सिर्फ बैठने के लिए. Also, मैं वेलकम करती हूँ वो डिग्नेटरीज जो ऑफ द डैश हैं और इस प्रोग्राम में उन सब का भी इस्तकबाल है. Lastly, a very warm welcome to our distinguished guest, Dr. Katrien Kolenberg. कुछ तकनीकी वजूहात की बिना पर वो हमारे साथ इस वक्त मौजूद नहीं है, लेकिन वो हमसे ऑनलाइन जुड़ रहे हैं. Let's begin our celestial journey by seeking blessings through the recitation of the Holy Quran. मैं तिलावत के लिए दावत देती हूँ PhD स्कॉलर कोमैल मुर्तज़ा.
A very good afternoon to everyone. According to Indian standards. أعوذ بالله من الشيطان الرجيم.
Prayer हो रहा है. अभी तो आधा घंटा.
Refuge in shaitan, in Allah from shaitan. بسم الله الرحمن الرحيم. In the name of God, the most gracious and the most merciful. أَوَلَمْ يَرَوْا الَّذِينَ كَفَرُوا إِنَّ السَّمَاوَاتِ وَالْأَرْضَ كَانَتَا رَتْقًا فَتَقَفْنَاهُمَا وَجَعَلْنَا مِنَ الْمَاءِ كُلَّ شَيْءٍ حَيٍّ أَفَلَا يُؤْمِنُونَ. Not the unbelievers see that the heavens and the earth were joined together as one unit of creation before we clothe them as under. We made from water every living thing. Will that not then believe? وَجَعَلْنَا فِي الْأَرْضِ رَوَاسِيَ أَن تَمِيدَ بِهِمْ وَجَعَلْنَا فِيهَا فِجَاجًا سُبُلًا لَعَلَّهُمْ يَهْتَدُونَ. And we have set on earth mountains standing firm, lest it should shake with them. We have made therein broad highways between mountains for them to pass through, that they may receive guidance. وَجَعَلْنَا السَّمَاءَ سَقْفًا مَحْفُوظًا وَهُمْ عَنْ آيَاتِهَا مُعْرِضُونَ. And we have made the heavens as a canopy well guided, yet do they turn away from the signs which these things point to. وهو الذي خلق الليل والنهار والشمس والقمر كل في فلك يسبحون. It is He who created the nights and the day, and the sun and the moon. All the celestial bodies swim along, each in its rounded course. وهو الذي خلق الليل والنهار والشمس والقمر كل في فلك يسبحون وما جعلنا لبشر من قبلك الخلد أفإن مت فهم خالدون. We granted not to any man before thee permanent life. If he though should die, would they live permanently? وما جعلنا لبشر من قبلك الخلد أفإن مت فهم خالدون كل نفس ذائقة الموت ونبلكم بالشر والخير فتنة وإلينا ترجعون. We granted not to any man before thee permanent life here. If then thou shouldn't, would they live permanently? Every soul shall have a taste of death, and we test you be by evil and by good, by way of trial. To us must ye return. Sadaqallahu al-Aliyyul Azim.
Thank you, Komen. Now let's resonate with the spirit of Manu as we proudly present the university song.
Saran tadi sa highly effective people who can break the together, which guarantee a product and its complemented secrets.
Now, I invite our Dean School of Sciences, Manu, to share some words of wisdom with us.
Thank you, Julia. Assalamu alaikum and very good afternoon. Welcome you all. Dr. Katrien Kolenberg, Professor of Astrophysics, Dr. Alim Basa, Section Head Physics Section, Professor Najam Sir, Professor in Mathematics Department, Dr. Priya Hassan, Program Coordinators, our colleagues and dear participants who have joined online with us and physically present here. On the behalf of School of Science Manu, it is my pleasure to welcome you all in the invited lecture by Dr. Katrien Kolenberg, Professor of Astrophysics, Q11 and University of Antwerp, Belgium, on the topic of RR Lyrae star cosmic lighthouse with a twist. I am grateful to Professor Kolenberg who accept our invitation to deliver a lecture on RR Lyrae star. Through this lecture, we hope to gain a deeper understanding about RR Lyrae star. We are fortunate enough to listen a lecture from the author of famous review article RR Lyrae star cosmetic lighthouse with twist by Professor Kolenberg herself. We are delighted that she joined with us online. To our delegates, I wish you to inform that our university, Maulana Azad National Urdu University, was established in 1998 and the School of Science was established in 2006, having only mathematics as a department, and the other departments, physics, chemistry, geology, and botany, were added to the school in 2014. Presently, we are running UG, PG, and PhD program in all discipline. The School of Science also running UG program in vocational courses from 2019, and I am happy to inform you that this academic session, the university started master program in vocational courses MVOC. The program under the School of Science in collaboration with Medicover Hospital, Hyderabad. We feel proud that Manu has international collaboration to contribute to the field of science. On this occasion, I am happy to inform you all that one of Manu faculty member, Professor Abdul Wahid, from the Department of CSIT and the Dean School of Sciences, Dean School of Technology, received a project with a mega grant, rupees 95 crore. Congratulate to him, and it's a proud moment for us. I hope we will maintain this pace in the future, and Manu will shine like a star in the sky. Thank you, one and all.
Thank you, sir. Now, I invite Dr. Priya Hassan, the driving force who has orchestrated this celestial gathering. Please share few words and introduce our guest.
Yeah, thank you. Thank you. So, hello everyone, and hi to Katrien again. You saw a small glimpse of our university, though it was unfortunate that you could actually come, but you will come. We will come and we will meet, that's for sure. So let's keep that for the future. So I'm really happy to welcome Katrien to us because Katrien is a unique scientist. I've always been fascinated by her because of the way she likes to combine science with art. And that is not something that is done very often by scientists. It is considered that arts is another thing and we have to just deal with the science part of it. But Katrien does a very beautiful job of combining these two, and we'll hear more from her. So just briefly about Katrien, like I said, her work lies in the intersection of scientific exploration and artistic expression. She obtained her PhD in astrophysics with focus from spectroscopy on Lyrae stars at the KU Leuven in Belgium. Later on, she conducted her research at the University of Vienna and the Harvard-Smithsonian Center of Astrophysics, interspersed with extended stays in Africa and Asia, to teach astronomy and create art. Currently, she's an established expert in variable star studies and astroseismology, professor of astrophysics at the University of Antwerp and the Free University of Brussels. She's professor of science communication, associate research fellow at the KU Leuven, as well as coordinator of national programs to teach STEAM. This is not STEM. STEM, that is science, technology, engineering, mathematics, but there's an A in between, which is for arts. So STEAM, in a space context, and an artist. Katrien is passionate about using astronomy as a tool for global development and art as a way to touch and reflect upon the human condition. So welcome, Katrien, and we're looking forward to hearing from you. Thank you.
Thank you very much. Good afternoon, everyone, or wherever you are in the world, if you're joining. Thank you so much. I am delighted and very happy to be here with you virtually, but as my colleague, Professor Priya Hassan, has said, I would have loved to be there in person. The flight to Hyderabad yesterday got cancelled because of the storm, and I really regret not being there in person. But I will do my very best to convey you the story of our Lyrae stars, and for that I will share my screen. Oh, excuse me, Priya, I think we need to enable screen sharing again.
Oh, sorry. Yeah, 1 sec, just a minute. Okay.
Yeah, sorry.
Where do I put it? Just a second.
Sure.
Yeah, so you can go ahead.
Thank you. Wonderful. So I will share my presentation and share the sounds as well, because there's a lot of sounds in there. Okay. Okay. Is this meeting being recorded? Is it okay if I record the presentation? Okay. Can you see my screen? Can everyone see my screen?
All is good. Yeah.
Yes, all is good. Okay, wonderful. Okay, great. So I will talk to you today about our Lyrae stars. Our Lyrae stars are stars that play a very particular special role in astrophysics. As you will understand very shortly, they are cosmic lighthouses, but there's a twist about their behavior. There are a lot of things that we don't understand fully yet. And as a bonus, I will also have you listen to some stars, including our Lyrae stars. But as Priya has mentioned, I like to bridge disciplines. And I also like to promote multi-sensory exploration of data, which means that we are not only going to look at data, but we'll also use our ears to explore these data. Now, my visit to India is happening in the framework of the BINA collaboration, which is the Belgian-Indian Network for Astronomy. And it's thanks to this collaboration that I could be here, that I could come to Pune, where I am now, that I would have come to Hyderabad. And within this framework of Belgian-Indian collaboration, a lot of great things have happened, including the work together on the telescope in Devastal. And I'm delighted that I am the last person within the current framework visiting. And this visit is focused also on bridging the field of astronomy to larger audiences. But today I will talk about our Lyrae stars, which is actually my scientific topic, but I'll also mention the fact that professional amateur collaborations as well as citizen science can be very fruitful within this subfield of astrophysics. So what will I talk about today? I'll first introduce you to the RR Lyrae stars, which is a particular type of variable stars, and they are useful. Then I will talk about some unsolved riddles that surround these stars. And in particular, there's a modulation, which is called the Tsarskaya-Blaschko effect, which we haven't been able to understand so far. Then I'll talk about space photometry, because within the field of our Lyrae research, the recent data coming from space have really meant a revolution for this field of investigations, because that allowed us to look at these stars that we've known for more than a century in a completely new light. Then I'll talk about other parts of exploration, because actually before I did space photometry, I've worked a lot on spectroscopy, and this is really a way to go forward as well in understanding these stars. And then I'll give some examples of potential collaborations and investigations to be done. And then I'll with astrosounds, which is the sonification of the stars. Now, to frame all of this a little bit, our Lyrae stars are a type of variable stars. And variable stars are stars that change their brightness over time. Now, this variation in brightness can be due to different factors. It could be intrinsic or extrinsic. In case it's extrinsic, it means that there's something outside of the star or on the outside of the star that is responsible for the change in brightness. For example, if you have a binary system in which the stars are rotating each other, orbiting each other, and sometimes they eclipse, then you will have at some point less light, at some point more light, and that causes variability. Another example is that you might have spots on the surface, such as our sun has spots. Some stars have bigger spots. And as the spherical object rotates, you might have a different view upon these spots, and that will also give rise to a variability. Then on the other hand, you have the intrinsic variables. And in that case, there's something inside of the star that causes the variability. You might have heard of supernovae, stars that at the end of their lives explode. And so that gives rise in an enormous rise in brightness. That's an eruptive variable. You also have novae, stars that occasionally show these big spikes in luminosity increase. And these are also eruptive variables. And then you have the pulsating variables. These are stars that change brightness due to pulsations or oscillations. In this case, the star, which you can consider as a sphere, it will change its shape and or its size. And that will give rise to changes in brightness. Now, this is what is happening for these RR Lyrae stars. Now, we humans, we like to classify things, all the kinds of variability that we see in stars in the sky. We've classified them into these intrinsic and extrinsic classes of variability. Now, if you look at the pulsating stars, there's actually many subtypes. This graph only shows a few of them, a few famous ones. But as the decades of this research have gone on, and this research is quite new, we actually have tens of variable stars and subclasses as well. And the RR Lyrae stars are part of this. Now, the story of these stars starts at the end of the 19th century, beginning of the 20th century, when studies of the sky were done, and it was observed that in certain regions of the sky, and particularly in clusters, there were these stars that changed in brightness over time. And here on the left-hand side, you see a picture of Solon Irving Bailey, who was an astrophysicist at Harvard College Observatory in the US. And he initiated sky studies, surveys of the sky, looking at globular clusters, and actually more of the sky as well. And they found these variables in clusters. They were called cluster variables. And what they saw was that these stars, they change brightness over time. Now here you see a more recent light curve. So you see the brightness and you see the star over the time scales of typically half a day changes its brightness. And this is quite extreme in the sense that the star gets 1 magnitude brighter between minimum and maximum. So this is something that is easily picked up on a photographic plate. Also, if you look at these stars through the telescope just with your eye, you will see them change. And you can see them change in the course of a few hours. So it's quite a drastic effect. And that's why it was noticed also more than a century ago. Here you see a globular cluster. This is M3. And this is an animation made by my colleague Zoltan Kolat based on pictures of this cluster. It is sped up, so you can actually see the stars change brightness over time. What we also did is, my colleague did it, he sonified the stars. So we took the light data and turned them into sound, so you can at the same time hear the stars. I will launch the animation now. You see that some stars are changing brightness. This movie is sped up. One of these blinks actually lasts half a day. And the sound is also accelerated so we can hear it. So these are our Lyrae stars. And yeah, they're cluster variables that initially, how they were called. But then there was also a star found that had the same properties in the field, quite a bright star. That star was called RR Lyrae, and it turned out to have the same properties as these cluster variables. So eventually, this class of stars was called the RR Lyrae stars, after its brightest star, the prototype RR Lyrae itself. Now, these stars play an important role in astrophysics because, as you see, they have brightness variations that are very easily picked up. And also their average brightness, it's almost the same for all stars. It's very, very constant, which means that if you see the star further away, you will see that its mean magnitude is higher. It looks fainter. So you can use these stars as distance indicators. They are standard candles, just like the Cepheids. Moreover, these are stars that are evolved. They are far beyond the stage of the main sequence. They are actually in the Hertzsprung-Russell diagram, they're on the horizontal branch. They have passed a giant phase. And that means that they are old because they are relatively low mass. They started out with masses of about 0.8 solar mass, we think. And now they are already post main sequence, which means that they're old. They are over 10 billion years, 12 billion years. So they are witnesses of our universe at a much younger age. So they're important to do galactic archaeology. And then also, they are considered to be prototypes of purely radially pulsating stars. You see that they change brightness. Now, we know now that they change brightness because they actually expand and contract. And as they expand and contract, they keep their spherical shape. So we call these radial pulsations. They stay spherical and they are in that way easier to model. So they are standard candles. We see them in clusters, but also beyond clusters. We see them in the field. And we actually see them in all parts of our galaxy. We see them in the disk, but also in the inner, the outer halo, and even in between the galaxies. It turns out that in between our galaxy and Andromeda, we see our Lyrae stars in between. So you see that these galaxies are actually much bigger than you would optically guess. And as such, they really give information about the structure, the evolution of our galaxy and the interactions with other galaxies. Now, if you look at their pulsation properties, here you see like a cartoon of the light curves of these stars. They can be subdivided into different subtypes. And we speak of the subtypes RRA and B. Originally, they were separate, but then it was soon understood that it was the same physical mechanism behind these light curve shapes. And then you have the RRC stars. The RRAB stars have the higher amplitudes. They are about or above 1 magnitude in light variation. And they also have the more peaked light curves. So it's less of a sinusoidal variation, but actually a very steep incline, a very steep rise in light, and then a gradual decrease in light. The RRC stars, on the other hand, have the more sinusoidal light curves, and they have the lower amplitudes. For all of these stars, the periods range between a few hours and about a day. And as I said, the variations are easily picked up. They're quite high. The reason for these different kinds of light curves is that there are different modes, pulsation modes in action. For the RRAB stars with the more peaked light curves, we have the fundamental radial mode, which is acting in these stars, which means that in this star, you have layers moving in and out, and you actually have like all layers moving out and then moving in. Mind you, this is not all at the same speed. So you might have parts of the star, like the outside, that moves faster than the deeper layers, but still the whole star is like breathing in and breathing out. For the first overtone, which corresponds to stars of this category RRC, you have a different situation. In that case, you have between the surface of the star and the core of the star, you have regions that move in opposite directions. So you have what we call a nodal surface within the star. And around this surface, the layers move in opposite direction. And this is what we call the first overtone, which is displayed here. Now you can imagine even more complex cases with higher overtones, like the second overtone, etc. They also occur in our Lyrae stars, but they're extremely rare. So in most cases, we are dealing with the fundamental mode or the first overtone pulsations, which we can derive from our measurements, from the shape of the light curves. And these are the most common types. But we also have a type of our Lyrae star that shows both of these modes simultaneously. In that case, we speak of RRD stars. So you have RRAB, RRC, and then RRD. And this D stands for double mode. These stars pulsate in both the fundamental mode and the first overtone. And here you see a light curve of these stars. So you have parts that are more peaked and others are more sinusoidal. You see this combination of the two modes frequencies in the light curves. Now, this is how such an oscillation takes place. So I show this animation, and actually I like this animation because it shows that there is a phase lag between the layers in moving inside these stars. So you see that as the gray layer is already going inside, you see that the yellow layer is following later. So you see that there's a phase lag between these pulsations in the stars. Now, why do the RR Lyrae stars oscillate? What is the cause of their vibrations? This is something that initially was not known. Initially, we didn't know that stars were pulsating. It could have been maybe binary explanation. But then in the course of the first 20 years of the 20th century, we figured out that there is a mechanism, like a motor, that drives the star to pulsate, to change its size or change its shape. And in the case of the RR Lyrae stars, this mechanism is called the kappa mechanism, sometimes also called the kappa gamma mechanism. This kappa is related to the opacity, and the gamma is related to the temperature. Now, kappa, I'll explain this kappa mechanism. Kappa is the absorption coefficient, is the capacity of a layer inside of the star to block incoming radiation. And so we put a parameter on that, we call it kappa, and we give a number to it. It gives the ability of a layer to block the incoming radiation. Now, in some layers of stars, it can be that kappa, that is absorption coefficient, which is a certain number for a certain layer, that it goes up as you compress the star. Kappa is a function of temperature, of pressure. Now, if you compress this layer, and if the kappa then goes up, this will support the pulsation. The reason is that if you compress a layer and kappa goes up, the layer goes to a smaller radius because you compress it. And the radiation that comes from inside, due to the fusion inside the star, it wants to get out. So you have a certain pressure by the radiation coming from the inside. But this compressed layer has a higher opacity, so it's going to block this incoming radiation, which means that the radiation is going to push this layer because it doesn't let the radiation go through. It's blocking more of the incoming radiation. And this radiation pressure will move the layer upward. It will actually push the layer to go upward. And so we had a compressed layer. The opacity has gone up. The radiation will push the layer back up. It will go beyond even the equilibrium state, and it will go to a higher region where the kappa will go down. And the kappa will go down. That means that the opacity will go down. The radiation will be able to go through the layer, and then gravity takes over and the layer falls back. It falls beyond the equilibrium radius, and it again gets compressed, and you again have kappa going up. So you have this constant motor of kappa going up and then down again, and that's what drives the pulsation, because in a star you have an eternal fight, an eternal battle between the radiation pressure from the inside and the gravity from the outside. And in these layers, actually, this battle is triggered because at some point you can have the pressure win, and then again the gravity wins. Now, what causes this variable opacity? That is that in certain layers in the star, you have partial ionization. So the star is a mixture of elements, and depending on the temperatures, you will have different degrees of ionization of the atoms, the ions in the stars. And you might, for example, have a layer in which hydrogen or helium are partially ionized. And this ionization varies when you compress the layer and when it expands again. And this is what gives rise to this variable opacity. So in a nutshell, we get variable opacity that drives the pulsations. And this is particularly so because we have partial ionization. Now, these regions of partial ionization, where, for example, hydrogen is not completely ionized, or helium, or even metals, depends on the temperature in this layer. And for example, you will find, for neutral helium and hydrogen, you will find these partial ionization zones in layers at about 10,000 K. For helium-2, once ionized helium, you will find it at 45,000 K. And for metals, of course, you will need much higher temperatures to have this partial ionization, 200,000 K. Now, if we go and look at just this hydrogen ionization, for example, which is, of course, hydrogen is a very abundant element in the stars, you can imagine that some layers will, at the right temperature, be partially ionized. But that's not enough to drive pulsation, because every star has these layers. But this layer should be situated in the star at a suitable depth. You can imagine, and if it's too deep in the star, this layer, that this radiation pressure might not have an effect that you will detect at the outside of the star, which is where we actually get the light from and will detect the pulsations. Also, if it's very high up, you might imagine that, you know, the layer will be pushed out and it might not entirely fall back. So you have to have a layer that is at a suitable position in the star, a suitable depth, so that it can drive this pulsation to be observable as well and to be maintained. And that is why you have a suitable combination of luminosity, of temperature, and of chemical composition that will give rise to such an effect as the kappa mechanism. And that's why in certain zones in the Hertzsprung-Russell diagram, what you see here is a simplified version of an HR diagram with temperature and luminosity. You see the main sequence, and you see in this diagram a zone in which this partial ionization zone is located at exactly the right depth, and this zone is called the instability strip. The RR Lyrae stars are located in this strip, the Cepheids, which have higher masses as well. Then you also have the white dwarfs. So all of these are located in this zone in the HR diagram where you can have pulsations through this kappa mechanism. Okay, yes. Now, our Lyrae stars are not the only pulsating stars. Here you see again an HR diagram. And you see the main sequence. What you see also, you see some evolutionary tracks, but you also see some zones, these elongated ellipses, in which we observe oscillations or pulsations in the stars. And it turns out that they are excited in almost all types of stars and in many stages of stellar evolution, because we can see them all across this HR diagram. For these stars, we will see periodic expansion and contraction or deformation of the layers of the star, and that can happen in different ways. So it can be very easy. It can be that the star is a sphere and remains a sphere, or it can be a bit more complex. You get deviations from a sphere. Now, how are we going to describe this? For example, for radial pulsations, I already showed you the modes in which our Lyrae stars vibrate. For a radial pulsation, it's quite easy to model. You say the star expands and contracts, but depending on how many nodes you have between the center and the surface, you might have a different radial order. That's the number of node surfaces. Typical stars that pulsate in such radial pulsations are our Lyrae stars, Cepheids, Mira stars, typically stars with high amplitudes. Then for non-radial pulsations, the motions are a bit more complex, and you see this here below. You see a sphere that is pulsating, and you see actually the deformations. In this case, we need a bit more numbers. We call them quantum numbers to describe these pulsations, and we are going to use spherical harmonics to describe these patterns of motions and these nodal lines on the star. Now, for non-radial pulsations, just like for radial pulsations, you have the radial order denoting the number of node surfaces between the core and the surface of the star. But you also have the other quantum numbers named L and M. L is the degree, that's the number of nodal lines on the stellar surface. And then M is the azimuthal number, that is the number of lines on the surface that pass through the star's rotation axis. And depending on how L and M relate and whether M is 0, higher or lower than 0, we speak of axisymmetric, retrograde or prograde modes. And that depends on how these waves move over the surface to the rotation. So if they move opposite to rotation, they're retrograde, otherwise they're prograde. And here again, you see for the value of the degree L is 3, different configurations. So that's how we describe non-radial modes. Now, you might wonder why is she talking about non-radial modes? Because our Lyrae pulsate in radial modes. Well, I do it because we're not entirely sure anymore that the RR Lyrae are only pulsating radially. It could be that they're also pulsating with non-radial modes, and in that case, we need to be able to identify these modes. And so we need all of this physics and mathematics to describe it. Now, if you look at the sun, it pulsates in many, many millions of non-radial modes simultaneously with very high degrees, azimuthal numbers and orders. And so in general, in our field of astrophysics that we call astroseismology, which is the study of pulsations of stars, the more of these modes that we can detect, the merrier and the happier that we are, because what we want to do is we want to find these modes identify them, then go back from these modes, and to each of these modes a frequency is associated, to the models of the stars, and to be able to model the star and to predict what kind of star, what kind of stellar parameters would cause these type of variations that we observe. And that's the field that we call astroseismology, which we apply to many types of stars. Here you see actually the variations of a star that vibrates like the sun. We call this solar-like oscillations, which is a topic that is very, very timely right now, because of course, looking for exoplanets around solar-like stars, it's very, very valuable if you can also, through the pulsations of the star that the planet orbits, get more information about the star. Because the better you know a star, the better you will know a planet. And so this seismology is very useful with a lot of applications in different fields, not in the least the study of exoplanets. But let us turn back to these classical pulsators, the stars that we've known since more than a century that are pulsating, and we have good reasons to investigate them. And I already mentioned that our Lyrae stars, that they are quite constant in their average luminosity. You see them here in this period luminosity plot. And you undoubtedly have heard about Cepheids being used as distance indicators, as standard candles, because they have a relation between their period and their luminosity. Depending on the type of Cepheid, you might have a different calibration of this relationship, but they can be used. If you know the period, you know the intrinsic luminosity, and you can derive the distance. For our Lyrae stars, this is also done. And this is very, very useful. It has allowed us, and this is work that actually started around the same time that the first studies of our Lyraes happened, at the same location. You see here a picture of taken at Harvard College Observatory. You see one man who was a staff astronomer, but you also see a lot of women. And these women, they worked at Harvard College Observatory as computers. They were very, very skilled in analyzing and computing based on photographic plates and the data. So these data that were taken also of our Lyrae stars, of Cepheids, data taken from the sky across the globe, because they had observatories in the northern and in the southern hemisphere, they were analyzed by these women. And there was one woman, Henrietta Leavitt, who was one of these extremely skilled women who looked at these plates, photographic plates, in a lot of detail. And what she found when she looked at hundreds, thousands of those plates, and she looked at, in this case, it was the Magellanic Clouds. So this is an assembly of millions of stars that were detected. And she looked and saw that some of these stars actually changed brightness. And all of these stars are in this Magellanic Cloud, so they're approximately at the same distance from Earth. And she observed that actually the brighter stars seemed to have the longer periods. And in doing so, so here you see the initial graphs that were published in 1912. And she wrote in 1908, it is worthy of notice that within this system of stars that she studied, the brighter variables have the longer periods. And this led to the so-called period luminosity relationship, which now, years ago, was renamed the Leavitt law after her, because she deserves the credit for this discovery, which actually opened up the universe for us and made it much bigger than we thought it to be. Because at the beginning of the 20th century, there was a big debate. We saw nebular structures in the sky, fluffy objects. And the question was, do these belong to our Milky Way, or are they further away? And using Cepheids in one of those fluffy objects, in one of these nebulae, allowed Hubble to prove that this object was actually, this spiral nebula, it was actually a galaxy outside of our own. So this made our universe much bigger than we thought to be. And that's just one reason to study these stars and to try and understand them better, especially for these classical variables. Now, of course, I mentioned the studies of the sun. And for the sun is the case for many other types in different phases of their lives. Different oscillation modes can happen, and they will penetrate the star to different depths. And if you have a good model of the star that you can perturbate and you can model the vibrations, then you can use the observations to study the internal layers based on the models. So you get the observations and you go back to the models and fine-tune the models to get better stellar models and much better handle on stellar structure and evolution through the study of these variable stars. So that's why we do this. And when we do this, we typically go and look at brightnesses. We take them over time. Then we go and check, do we actually, can we identify different modes? Can we figure out what type of pulsation is responsible for different frequencies? And at the end of my talk, I'll come back to this as well. But let's go back to our Lyrae itself. So this star is the prototype of the class. And I will now focus a bit on this prototype because it's a star that I've been studying for more than 20 years now. And before me, many people have gone before and studied this star. And every year, every decade, we unveil a bit more of this star. Now, this is a paper that was published in 1913 that reports on the first discovery of a star called RR Lyrae. It was called a cluster variable because, as I mentioned, we see a lot of these stars in clusters. And it was written by the author of this paper, Tucker, that it was discovered by Mrs. Williamina Fleming on a multiple exposure photograph. So she saw this variability. And they saw that this star had the same properties as the stars in the clusters that they had seen before in the studies of Bailey. And this is Williamina Fleming. She deserves the credit for finding this famous star. And she got these data. And these are the data from this paper from 1913. And these are the data of RR Lyrae. What we've done with this data is we have taken the light variation over time, and we have made a phase plot of it. So we have derived what is the period of the star, and then we have binned them. And what you see here is how the star varies between maximum light and minimum light. You see that here you have something that's comparable to the V magnitude, so the visual magnitude. You see that the star varies between 7th and 8th magnitude. So it's not faint, but it's not visible to the unaided eye. Now, I want to compare this plot that was taken over a century ago with data that I gathered of the star in 2003 and 2004. And this is an animated GIF. The red curve is an average light curve. And the blue are data that were gathered by multiple observers. Half of them are actually amateur observers with their own telescopes and equipment. And you see the data binned always over about four days. So every blue still image are data overplotted, gathered over 4 days. And you see that this star, actually, the curve of variation, it changes a lot. It changes over time. And that you have this average light curve. That's how the star changes on average. You see that actually as the time evolves, that the light curve shape changes, that the amplitude changes. So the difference between minimum and maximum gets bigger. The slope changes, the shape changes. You even see that the timing of the maximum changes. So sometimes the maximum will occur earlier and sometimes later. This effect is called the Blaschko effect. And this effect was discovered by Sergei Nikolaevich Blaschko in 1907, so more than a century ago. And what it comes down to is that the star, which has this pulsation period that takes on average half a day, it is modulated. It is modulated with a longer period. a period of typically tens of days, but it can vary between a few days to tens of days. That's typical, sometimes even hundreds of days. We call this longer period the modulation period or the Blaschko period. And during this longer period, we see amplitude and phase modulation. So the height of the light curve changes, also the timing of the maximum, the shape changes. And this effect is actually very common. It occurs in, as we know now, that's some new discoveries over the last decades, about half of the RRAB stars, so the stars with higher amplitudes among the RLRs, shows this Blaschko effect. So it's really common. It's quite puzzling because we don't know yet why it's happening exactly. Now, I want to make a small footnote here because Blaschko is credited for this finding. He published this in a journal called Astronomische Mitteilungen in 1907. But this paper, when it was translated, actually it mentioned that the data were gathered by Lydia Tseraskaya, so a female astronomer who got these data, and that's why we would advocate for naming this effect, the Blaschko effect, from now on, the Tseraskaya Blaschko effect. Just like we now renamed the period luminosity relation after Henrietta Leavitt, the Leavitt law, or just like the Hubble law now is called the Hubble-Lemaitre law, because the Belgian priest Lemaitre also contributed to the realization of the expansion of the universe. We would advocate for changing the name of this effect. So this is something that my colleague Don Kurtz, who wrote a very, very good review on pulsating stars in general, that I warmly recommend. And this is a text box from this article that he wrote 2 years ago, advocating for this renaming of the Blaschko effect after who found it. And so what was found was that this star actually doesn't always show a maximum at the same time for the first star for which they found it. They saw that sometimes the maximum occurred earlier and sometimes later. Later, when we got more and more data, getting entire light curves, you could see that actually the whole shape of the light curve changes, and also the amplitude. Okay. Now, I mentioned that it was found originally by looking at the timing of the maximum. When Blaschko and Tseraskaya were observing, they knew that these cluster variables were really, they were really predictable. You could, if you know the period, you can say when the next maximum occurs. And that's why they started doing these observations around maximum light to catch the maximum. And this kind of analyses that keep track of a certain epoch, a certain timing in the light variation of an object, say the minimum or the maximum, depending on the variable or an eclipsing binary, or we call it O minus C analysis. And this O stands for observed and the C for calculated. So what is done in these studies is that you go to observe a phenomenon, say the maximum of the light of a star, and then you compare it with when you would predict it to happen, which is the calculated timing. Now, then you can generate diagrams like shown here. If your O minus C is always 0, that means that you really know the period, that the period that you know is correct and it's constant. So you'll have a flat O minus C diagram. If, on the other hand, your O minus C diagram shows some slope or some changes, then there is something off with either the period, your knowledge of the star. For example, here, if you see a change, an increase in this O minus C, you know that the period is incorrect, but it is constant. You got a period wrong. And depending on the slope, you might have your period too short or too long. If you have not just a slope, but you actually have like a non-straight line, that means that your period is changing, that it is increasing or decreasing, and that could be due to evolution. So if it's just a star that is responsible for this behavior, you can detect period changes in this way. Now, lately, of course, we have data of this kind of stars since they were observed more than a century ago. So for some stars, we have O-C diagrams spanning more than a century. And sometimes you see even abrupt changes. You see changes that the star has from one period to another. Sometimes you see much more chaotic changes. And right now we are looking into these diagrams because sometimes we have them available for over a century, because actually if you have a binary star, it might also be detectable in these O-C diagrams. Because not only the period of the star itself can change, but if the star is in a binary system and you don't see the other component, then sometimes your star will be closer to you and sometimes it will be farther away, which means that sometimes you will detect a maximum sooner and sometimes later. So you will get a variety in this O-C diagram just because of this light time effect in the orbits. And with PhD student Salma Silla, who is currently also online, so she's attending this talk, we are currently investigating this for certain stars that show weird O-C diagrams to figure out whether there could be a binary component. So without even seeing this component, from the knowledge that we have of the star, we could derive the properties of this binary, if there is one. So this is work that is based on very simple observations, often done and now continue to be done by amateur observers. That is very valuable to really get to the core of what we know of our Lyrae stars. Because puzzlingly few our Lyrae stars are known to be in binary systems. And this is a way to figure out and to find more of these potential candidate binaries. Now, of course, if you have a Blaschko effect, that will also have an effect on your O-C diagram. You will also have a change in the timing of the maximum. And through these O-C diagrams and through further studies in more detail, we know now that the Blaschko effect is not always regular. That, we see in the Lyrae stars, we see these changes in periods, but also the Blaschko period changes. Sometimes we see that stars have changing cycles of the Blaschko effect, and I will show that in a few minutes. We also see in many stars that it's not just this modulation taking place over tens of days. I will go back to the slide of the Blaschko effect, this one. So here it's put very simple. You have one longer modulation period, but in some stars we see even an overarching longer periodicity of the order of years. And so all of this has to be taken into account when we consider this modulation of these stars. Now, Blaschko is very common in our Lyrae stars. The Tseraskaya-Blaschko effect is super common. You could wonder, do other radially pulsating stars show this as well? There's been several papers published by colleagues who study other types of variables like Cepheids, like high-amplitude delta Scuti stars, all stars that pulsate with radial modes. And for several of them, we see modulation as well. And the question is whether it will be due to the same effect, the same cause, or not. Now, this Blaschko effect is something that has been puzzling me and my colleagues for decades now. And of course, since it was discovered, many attempts have been done at trying to explain this phenomenon. There have been different models, including magnetism, convection, resonances, different combinations of these effects as well to explain this behavior. And these models, because we don't know what the final model is so far, have evolved over the years. When I entered this field, there were two popular models for the modulation that we see. One involved resonances and the other one involved a magnetic field. And so both of the models had, advocates for the models. There were papers with detailed mathematical physical descriptions of how this could cause a modulation in the star. In the resonance model, it was seen that there was a resonance between the radial mode, the one that is very, very prominently there, and then a non-radial mode of a low degree, maybe L1, and that would cause these modulations. For the magnetic model, there would be a magnetic effect, so there would be a magnetic field that causes this. And both of these models involved non-radial modes. That's why I spoke about non-radial modes, because in the models as we knew them, it seemed necessary to involve these non-radial modes, these deformations of the surface, to get to the modulation that we see. But they had different predictions. For example, and let me go to the resonance. Resonances, we see them in nature, we see them in stars as well. But for our Lyraes, we know that the radial modes, we can predict the periods. These could not be responsible for what we see in the star, because the periodicities that we saw in the modulation were not plausible for just radial modes. So it had to be a non-radial mode of a low degree, and that would give rise to this amplitude modulation. And the predictions that were made was that if you would take the light curve and you would analyze it, you would do a frequency analysis in the spectrum, you would see triplet components. So you would see additional peaks, additional frequencies around the main frequency. And there were different authors that elaborated on this model. Then on the other hand, the magnetic models, and I show them just to show you, to demonstrate, how we do science on these stars and how science evolves. Even in the time frame of a few years or a few decades, you see a whole range of models that come that seem plausible and that then have to be either proven or disproven with the help of more data. For these magnetic models, they are reminiscent of models that we use for other objects as well. So what we have is a magnetic field. So you have a magnetic field, and this magnetic field has a certain orientation in the star. Now, the star is a spherical object. It's rotating always. It has a rotation axis. But this star could have a magnetic field that is off, that has an inclination with respect to the rotation of the star. And so you would have a magnetic field that is not oriented with a rotation axis, but at this off axis. And this magnetic field would deform the star to have additional non-radial components. So you have the radial modes expanding and contracting, but on top of that, you will have a deformation by this magnetic field that would give rise to what we call quadruplet components, or this quadrupole modes with L equals 2. And as the star rotates, you would get a different view on this deformed stellar pulsation. And you can then from that infer that you would get a change in the total amplitude of the light curve. So this is the prediction of the magnetic model. But of course, you would need a magnetic field for that. Another prediction of this model is that because you have these quadrupole components with L equal 2, in the frequency spectrum, you will see quintuplet components. So next to your main mode, you will see small peaks of frequencies, 2 on either side. So this is what we call a quintuplet component. And that was a nice prediction of this model that could be verified analyzing data. And again, we had some papers that backed up this model, that explored this model. And also there were parallels made with other stars that have the same kind of effects. But of course, you need a magnetic field for this model. And the original papers said that you needed a field of at least 1 kilogauss to cause this deformation of the radial mode. So then the question was, do we actually see a magnetic field in these Lyrae stars? And then if we go back in history and look at magnetic field measurements for our Lyrae stars, they have happened, but mostly for the brightest star, because for magnetic field measurements, you need to get good spectra to detect magnetic deformation, a Zeeman effect. And for that, you need a lot of flux. So you need a big telescope and you need a bright star. And our Lyrae itself is by far the brightest star. So for this star, we got data. And through history, there were authors who detected a magnetic field and others who said, no, there's nothing. Because it's not so easy to do a spectroscopic analysis of these stars, because the star is pulsating. And as the star is pulsating, you have the spectral lines moving back and forth. You get broadening of the spectral lines that could be confused with a Zeeman effect on the lines. So it's not so easy to really extract a magnetic field from these lines. The last measurements that were done by Mariam Shadid et al. Said, no, there's no magnetic field for our Lyrae, at least. Then in 2008 and 2009, I did a study together with colleague Stefano Bagnulo, looking at several stars, so not only our Lyrae stars, but using a much bigger telescope, using the Very Large Telescope in Chile, 8-meter telescope, and using an instrument that combined different spectral lines. We observed a few tens of targets, and we had some stars that were Blaschko modulated, others not. And we tried to see, do some of them show a magnetic field? And none of them showed a convincing detection of the magnetic field. So for us, that meant that the model in its form as it was not so viable. After, and in all of these discussions going on what is the cause of the Blaschko effect and all the testing, another model was proposed by Richard Stodders that said that, because in these stars you might have variable turbulent convection in the star, in the outer layers of the star, and that could also give rise to modulation. So, if models don't really prove that, if a model doesn't prove to be completely waterproof or completely apt to predict what's happening, then of course other models will come up. And that's what has happened for our Lyrae stars in the last decades, especially with the advent of new data. Because there were a lot of problems for these initial models. And we saw a lot of facts when we analyzed the data. We saw that some of the predictions of these models were not really held when we looked at the data. And so there were some questions like, looking at the spectra, we would see sometimes triplets, sometimes quintuplets, so we could not really get a clear idea of what is it now. We would also see that depending on the population of stars, you might see less and more Blaschko effect, less Blaschko effect for long period variables, etc. So these models were insufficient. That's why other models came up, like this variable turbulent convection. But then actually we got Kepler data. And I now briefly expand a bit on how we analyze the data. I've already talked about Fourier analysis, frequency spectrum, but for some of you, it might be useful if I just give a short overview of how we analyze the data. So what we get is light curves, so you get a variation of the light, the brightness of the star over time. And from this, you can derive the periodicities. And you have the periods that you get all out of these data, and the amplitudes. And these periods and amplitudes, and for this light curve shown here, it's very simple. You have one period and one amplitude. It's not changing. The same difference between minimum and maximum, but most of the times it's more complex than that. And we then do a frequency analysis. So we go from this time domain, we go to look for what periodicities do you see. Now it's just one period. Like in this case, you will see one peak. And since this is a very nonlinear curve, a peaked curve, you will also see the multiples of that curve. Now for a random variable, typically you will see some peaks in the frequency spectrum. And the higher the amplitude, the more prominent this frequency or this periodicity is present in the data. So you here have the amplitude, could be expressed in magnitudes. And here you have a frequency. You can use whatever unit, inverted time here. Here we use cycles per day, because that's the unit we very often use for our Lyrae stars. And here you see a typical frequency spectrum for such an RR Lyrae star that has a very peaked light curve with one period. So we have this period here. This is a star that pulsates every half day. So you have 2 cycles per day as the main period, as the main frequency, half a day as the period. But because this light curve is so peaked, you also see the multiples. You see 4, 6, 8, etc. cycles per day. So this is a typical Fourier spectrum for a non-modulated RR Lyrae star. And you can see these harmonics, these multiples of the main frequency up to a very, very high order. Now, if you look at a modulated star, we will see something more. You will see this frequency and its multiples, but you will also see small peaks appearing next to the main frequency and its harmonics. And we call these multiplet components, and they can come in different forms. So sometimes you see just one peak next to it. Sometimes, if you have more data, better quality data, you will see 2 on either side. Sometimes you even see 5, or even you see 2 on either side, or you see even 3, 5, etc. if you have really good data. So what is typical is that you see these side peaks. Very often they are asymmetric, so one is higher than the other. And as is shown here, some colleagues, even in the data that I analyzed myself, sometimes we saw much more. We saw septuplets, nonuplets, etc. So none of the models predicted that either. Now, this is what we get from the from photometry. If you have good data, light curves over a long time, you can get these spectra and you get these side peaks that give you an indication of the periods. But of course, there's much more than photometry alone. You can also look at spectra of these stars. And here you see a plot from one of the first papers by Preston, Smack, and Paczynski from 1965, where they analyzed a combination of spectra and photometry. So you see variations in the V filter. Also, they use different filters, so you can see a change in the color of the star if you use the color index. But they also detected emission. So they detected an emission in the spectrum. So they detected hydrogen emission in certain phases of the star, close to the maximum light. And they also saw that from the spectra, you can get very good radial velocities, and you can get basically a mirror image of the light curve in the velocities. Now, all of these details that you get from the spectra, they show us that our Lyraes, they also need to be studied with spectra, because they have very tumultuous atmospheres. And there are models of these stars that describe these shock waves in the star, for example, nonlinear pulsation codes that can describe these variations. And as I showed before, you have a phase lag as well between the different layers. And this is something that you can only investigate if you do spectroscopy. And this phase lag is called the Van Hove effect. So when I did my PhD 2 decades ago, and I was studying these are Lyrae stars, trying to figure out what could be responsible for the Blaschko effect, I looked at spectra. And I tried to see, like, what are the phases in which the star is calm, and in which phases do you have really shock waves going through? How could, from the calmer phases, we derive something about this Blaschko effect? And so if you look at spectra of a star, what you get is spectral lines. And here you see one spectral line. We zoom in on it. Of course, if the star is pulsating, then you will get a Doppler effect on the spectral line. So the spectral lines will move back and forth in the spectrum of the star. And this is something that I did for my PhD. At the end of my talk, I can briefly expand on that. But this is really the way forward if you also want to go and look at what are the typical pulsation patterns in these stars. Because the spectral line moves back and forth, of course, because of this pulsation, but the shape of the spectral line is actually an image. It's a representation of the shape change of the star. And if the star has a non-radial oscillation component, then you will see this pattern in the line profile. So you will see variations of the shape of the spectral line, what we call line profile variations. And you can, from these changes of the spectral line shape, derive what kind of deformation is this surface of the star undergoing. Now, RR Lyrae stars have been studied with spectroscopy, with photometry, and mostly with photometry. And what I now showed so far were dedicated studies. So just looking at these stars, measuring their timings, getting spectra, trying to understand only these stars. But within our field of the RR Lyrae stars, classical pulsators, we have made a lot of progress just benefiting from other kinds of surveys. For example, microlensing, people looking for dark matter. They have to look at the sky, keep track of changing transient events, changing brightnesses, and in doing so, they will also capture the variations of an RR Lyrae star. So we got hundreds, thousands of data from microlensing surveys, such as MACHO, OGLE, which has observed tens of thousands of RR Lyraes, and other large photometric databases. But a very big change for our field came, so we got a lot of numbers, a lot of statistics from these surveys of the sky. And then more recently, we got very high precision, high cadence data from satellite missions that were focused on observations of stars, sometimes to find exoplanets, sometimes to really just study the pulsations and the rotation and the convection of these stars. And I want to highlight one mission because this mission for my field has led to some breakthroughs, and that is Kepler. Kepler was launched in 2009, looking at a field in the sky just outside of the disk of our Milky Way, but close enough to have a lot of stars that might resemble our sun. And in these Kepler fields, we had a variety of stars that were interesting to find exoplanets, but also stars that were interesting just to do variability studies. And so for this Kepler mission, before it was launched, we set up a collaboration called the Kepler Astroseismic Science Consortium, the KASC, in short, with a few hundreds at a time, about 500 scientists, including myself, who would just look at the pulsations of the star. So not looking for exoplanets, but just looking at how do the stars change over time, because we knew that we had never had such good data ever before. The precision of Kepler was really fine-tuned to find small planets around solar-like stars. So we knew that with this precision, we would get unprecedented data of variables. And these allowed us to do data analysis, to do modeling, and also for some of the stars to initiate ground-based follow-up, to get a much better handle on the stars. And so I've been chairing the RR Lyrae working group for more than a decade on these stars, together with my colleague Robert Szabo from Concoli Observatory. And within this working group, which has a few tens of members studying just these stars, we combine data analysis with modeling and also ground-based follow-up. So everyone has their specialty, and together we try to bring the pieces of the puzzle together to understand these stars a bit better. Now, looking at this data, here you see two types of light curves. For an RR Lyrae star, you see here the typical cadence of Kepler is one data point every 30 minutes. So for a star that pulsates once every 12 hours, you get enough data points to see how the light varies. But then for a select number of stars, the ones that are really interesting also to find exoplanets, we get short cadence. And short cadence means that you get data every minute. And that will give you a much better view on the light curve. So you see here, you see that in some, you see, of course, the light variation. Something that we would miss with a long cadence is that you see even changes in the slope of the light curve. You see small wiggles. And each of these, of course, have something to say about the inner physics of the star. This is linked to shock waves in different layers that influence the luminosity. So this is interesting. And we had never had such great data before. Of course, to get 1 minute cadence, this is expensive in the sense that not many stars get this cadence. So we really had to apply for certain stars to get a few months of data just really in so much detail. The priority was given to exoplanet targets, but some of the astroseismic targets, some of the pulsating stars also got this priority. And so that's why for a lot of our Lyrae stars in the field, we also have these data. And now I want to zoom in to what Kepler brought us. We got about 40 stars that turned out to be our Lyrae stars. And we did, before the mission was launched, we looked at the field, we looked at old catalogs and looked at previous classifications, and there were about 150 candidates, of which more than 40 turned out to be genuine Lyrae stars, bona fide Lyrae stars. And here you see the data in long cadence for some of these stars. You have stars that are nicely repeating, very well behaved, clockwork pulsators, but then you also have about half of them, as we could predict, Blaschko stars. So stars that show this Tseraskaya-Blaschko effect. For the stars that were well behaved, you saw no change at all. So whatsoever, they would be totally repeating, very, very clear at this lower than millimagnitude, 1/10 of a millimagnitude level. But then some of the stars are clearly modulated. Here you see data taken over a few months, and you see the envelope shows how this star is modulated. The star actually vibrates very quickly between these extrema, and you see that the amplitude changes. From the data themselves, we can really analyze this Blaschko effect. And if we stitch together different parts of the data gathering, we can get to very nice light curves that allow us to study these effects in a lot of detail. For stars that have changing Blaschko cycles, like here, but also for stars with very nicely behaved repeating Blaschko cycles, such as the one here. And then, to come back to the beginning of my story, our Lyrae itself was located in the Kepler field. So the star that had been found more than a century before was located exactly in this field, because the field of Kepler is between Cygnus and Lyra. And we knew that our Lyrae would be in the field, but we were told that Kepler is optimal around, for stars fainter than 10 magnitude V. And our Lyrae is much brighter. So we thought it's going to be too bright to be observed. And effectively, here you see the star on the Kepler CCD, it's heavily saturated. It bleeds over. It's very hard to reconstruct the light curve. Yet we did get a light curve for the star, and what we saw was so interesting. We immediately saw this must be our Lyrae, and we saw some effects on these truncated light curves that was so interested that we went back and spoke to people at NASA, and in particular Steve Bryson, who did the photometry for the Kepler mission, and we asked him if he could help us to reconstruct a light curve, because if you just use the saturated aperture of the star to do photometry, you will not get all the flux. So he spent quite some time. He got very excited by our motivation to try and reconstruct the flux, because we saw some effect that we had never seen before. And after some time, he devised a custom aperture for the star that would allow to look at pixels that were not saturated, never all saturated, to reconstruct the flux in the saturated pixels. And doing that, that allowed us to really reconstruct a light curve. And that's what you see here on the right. So these are the Kepler data that we got from the first sets of data that Kepler were downlinked from Kepler. And I compare this with data that I gathered several years before, just 5 years prior to that, using ground-based observatories, collaborating with colleagues across the Northern Hemisphere, some of them amateur observers, 7 different observatories. And we got this super nice light curve, which I thought this is the best ever. I spent quite some time, more than a year, stitching together the data and making sure everything was well brought together. And then I got this fabulous spectrum that you see here, which gave us a lot of information already. But then, just for free, 5 years later or 6 years later, we got this without even expecting we would get it. We would get this beautiful light curve with very high cadence, no interruptions, every half an hour data point. And after the light curve was reconstructed with the help of Steve Bryson, we got this super nice frequency spectrum. And so this is what just a few years did, but observing from space. And now I will zoom into this light curve that you saw on the right, this one. And this is the paper in which we report on this. If we zoom into this one, and particularly on a part where you clearly see the Blaschko effect, that's what you see here. And what Kepler revealed was that actually you don't only see a Blaschko effect, you see alternatingly higher and lower maxima within this modulation. You see here, this maximum is higher, this is lower, this is higher, this is lower. And that's something that, as big as it is, here you see that it's like 5/100 of a magnitude, which is something that we can easily measure from Earth. But we had never seen it before. Now, this up and down effect, if you do a frequency analysis, up and down comes down to a double period. And a double period comes down to a half frequency. So what we got in the frequency spectrum of our Lyrae were half integer frequencies that were a manifestation of this period doubling. And this was published because this was the first time that we saw this. We then studied it in more detail, and we saw that actually this up and down effects called period doubling, that it was clearly there, but it was not always there. Here you see 3 consecutive Blaschko cycles, so just consecutive months. Every cycle takes about 40 days. And you see that, yeah, it's a bit chaotic. Sometimes it's clearly there, sometimes it's clearly up and down. Here it's not so clearly up and down. Here it's more like a gradual increase. So its strength varies in a chaotic way. Now, of course, it's interesting to see it, but why is it there? So what is the reason for this period doubling? And when we first showed it to some members of our team that are into models of the star, one of my colleagues, Paul Moskalik, he said, this effect, we have predicted it for Cepheids, but we've never seen it. This is period doubling, and it's caused by a resonance within these stars, a resonance between radial modes. And so now we had never predicted it for our Lyraes. We had no clue it would be there, but we saw it. So then going back to the Cepheid models and adopting the similar effects for our Lyrae models, it was shown that, that actually even in our Lyrae models, this could be predicted. It had never been observed nor predicted in models, but it had been predicted for other types of stars with similar light curves. And if you go into the models, and this is done in the paper that is cited here, then this period doubling effect could be explained by a resonance between the radial mode and a higher order overtone mode, but a radial mode as well, a resonance between 2 types of radial modes. And my colleagues, Zoltán Kollát, László Malor, and Robert Szabo, they calculated potential frequencies for these overtones, depending on the combination of the parameters of the star. And they saw that in some cases, there would be a resonance that could give rise to this up and down effect. So that's the explanation that we have now for this period doubling effects. Now, why was this period doubling never seen before? You could wonder, because it is quite strong. Sometimes from one cycle to the next, you might have a difference of 0.1 magnitude, which is very, very big. Well, it was never observed before because we were always observing from the ground. And if you observe from the ground, you have a day-night cycle. And these stars have typically periods of 12 hours. So if you catch a maximum during one night, the next maximum will most likely fall during the day, unless you're observing from the poles. So you would not see this alternatingly high and low effect. And sometimes we use different observatories at different longitudes, but still, you know, stitching together the data, we didn't pick it up. We didn't see this period doubling. So there's some kind of exclusion principle just because of the rotation of our Earth that made that we needed space to get this. Now, as I said, in Cepheids, it was this radial resonance that gave rise to this period doubling. So then my colleagues started to do modeling hydrocodes, and they could also predict the onset of period doubling in our stars.
Sorry to interrupt, Katrien.
Yes.
We need 5 minutes more.
Okay, that's good. 5 or
5.
Okay.
5 okay.
Okay, thank you. So this effect, we could predict it. Now we know what it is due to. And this model, this period doubling model, actually led to a new model for the Blaschko effect. Because if you can cause period doubling, it turns out that you could also cause modulation. So this new data gave rise to a new model, the radial resonance model for the Blaschko effect. Now, following that, using the Kepler data, we also ruled out some models, and I will not go into the detail of that, but I want to just give you the bottom line, and that is thanks to the very detailed data, we could rule out some models and come to the conclusion that most likely this radial resonance model that is responsible for period doubling could be responsible for the Blaschko effect. Now, looking at the stars in the Kepler field, you see many crazy stars that really challenge our understanding of our Lyrae stars. And that's why we do need additional data. So we do get spectra of these stars to get a better handle. And now that we have K2 and TESS, we have many more of these data. We actually have too many data to really analyze one by one. So we do ensemble studies. And of course, there's a lot of great data for students to work on. To end my story of our Lyrae, I want to just get back to where I began with our Lyrae. And I want to show you this image, which looks computer generated, but it's actually just data gathered by Kepler in short films. And if you compare that with data that were taken a century earlier that I showed, these data taken by Williamina Fleming, published by Tucker in 1913, you see how far we have come just in 1 century, and how now we have a much better view that allows us to enter a new era in the studies. And as we enter this new era, of course, there's a lot of new question marks that have to be answered. And therefore, other kinds of studies are useful too. So we continue to get these data from space, but at the same time, it's very valuable to keep on doing multicolor photometry, time series spectroscopy, get data in other ways like X-rays, interferometry, to gather more. And in the past, I've had many collaborations also with amateurs and also with people with small telescopes. Here's a telescope that is used in Morocco to get spectrophotometry of our Lyrae stars. There's examples of tiny telescopes following our Lyrae. And then finally, I want to point out a work I will go through this, of Salma Silla, because she's here, who's now working on analyzing these O-C diagrams, O-C diagrams to figure out whether some of these stars might be binaries. So there's so much more work to do beyond the space photometry, which has taken I think the scene in the past decades. Now it's time to get back to really detailed studies. And Salma is here. She is finishing her PhD thesis on this very interesting work using very old data gathered by many people over the past century to look if we can find long period orbits of stars. Now, to end with, I promised you a bonus, and that bonus is about astro sounds. Do we still have some time, Priya, to do that? Then I'll stop sharing my screen. I'll get my presentation. Okay, I will share the stellar sounds now, which is the bonus. Okay. Yes. So I want to say a bit about Astrosounds. Astrosounds is a project in which we have taken light curve data of stars, so what I explained to you in the past hour, but we turn them back into sound. And yeah, we use light, obviously, but now we get back to sound. And you know that sound needs a medium in space. Sound cannot really travel through empty space, but yet we can get data through light. And we humans, we hear in a very limited range. We hear between 20 and 20,000 vibrations per second, or hertz. And stars, they vibrate. I just told you that, but they vibrate much more slowly. And so the sounds that we have on Earth that we can hear, they are easily audible, but for stars, we will have to speed them up. Now, I just explained to you in my presentation how we can see the stars sing, because as the stars contract and expand, they will get a change in their brightness. And this is something we can record with cameras, telescopes, our eye. And what we get is that every star has its own light curve. Every star has its signature within the light curve. And this light curve is, in most of the cases, definitely in the stars that I talked about today, is a result of acoustic waves inside the star. So you actually have sound waves inside the star that then are changing the light output of the star. So you could actually go back from these data that we get, for which we gather the frequencies in the ways that I showed you. So we get the frequency spectra, and then we can speed them up and bring them back into the audible range. So what Astrosounds wants to do is to see if we can use sound to see better. If you use sound combined with images, or for people with visual impairments, if they can listen, they can pick up a lot of information about the object. And in Astrosounds, we have looked at what could be good ways to sonify the data. And I'll give you an example for a star that vibrates like the sun. Or like vibration, sonified. Another example within Astrosound, we like to, because we target a large audience, we like to work with stars that people might be able to see in the night sky. For example, one of the most famous stars is Polaris, the northern star, which most people, or a lot of people, can find in the sky, and which most people know it has a specific role in our cultures. But at the same time, many people don't know that it's a pulsating star and that it's a Cepheid that vibrates every 4 days. And this is what it sounds like. So that's the sound of Polaris. Then another star that is not so far from Polaris in the northern sky, which actually, because of the precession of our Earth's rotation axis, will become the new northern star in a few millennia, is Beta Cephei, or Alphyrk. And this star is an early type star. It's hotter than Polaris, and it's still in its main sequence phase, and it can fuse heavy elements as well. And so this has a very distinctly different sound. And then finally, of course, since I talked to you about our Lyrae, I want to also bring that star to the forefront. Here you see a sped up video of the star. One of these blinks takes 13.5 hours, but if you sonify it, including the Blaschko effect, it sounds like this. Yes. So that's the sound of our Lyrae. So in short, in summary, there's a whole cosmic orchestra. And in Astrosounds, we want to make that audible to a large audience. Astrosounds is a citizen science project, and we got funding for this from the Flemish government to make a platform and a website and to make educational material to bring these sounds of stars to a larger public. And my idea, or my goal behind this, is to investigate, by having many people listen to stars, how people perceive these sounds. So we have a website, it's called astrosounds.be, And there it's translated in English as well. Meanwhile, you can make an account and you can also do experiments yourself. And in doing so, you can learn about things like pitch and timbre. And at the same time, you can test your ears and train your ears to get better at hearing different things. So we also have, we do outreach also in public spaces. We have a booth where you can listen to the stars and take part in experiments there. And importantly, we have STEAM or STEM education modules. The STEAM stands for Science, Technology, Engineering, Arts, and Mathematics. So we also want to bring in the creativity and the artistry of young learners to make them learn with more enthusiasm and to make the things stick better. So we have modules on programming star sounds, making your own orchestra, and we spread those. And finally, yeah, we do this because astronomy is a science that is a science for all. And if you use multimodal or multi-sensory exploration of data, you will make science much more inclusive and have people with different abilities and with extremely precise hearing be part of this adventure. I'm sure we will get new and interesting results. And yeah, with this, I would like to end my talk. If there's any questions, I'll be very happy to take them. Thank you very much.
Yeah, so thanks so much, Katrien, for that lovely talk. Do we have any questions? Does anybody want to ask something? I think people need to check out your website. And
yes.
And then we do that. So thanks a lot, Katrien. And
Thank
you. Yeah, your video.
Thank you, ma'am.
Thank you.
Now, let's express our gratitude. I call upon Mohammed Tayyab, PhD scholar, to deliver the vote of thanks.
Assalamu alaikum and good evening to all. First of all, I would like to thank Almighty Allah that He let me and all of us be a part of this wonderful program and guiding us through this celestial journey. Our sincere appreciation goes to our esteemed guest, Dr. Katrien Kolenberg, whose insights have illuminated our understanding. Thank you very much, Madam, for the wonderful and insightful talk. I extend my deepest thanks to our Honorable Dean, School of Sciences, Professor Salman Ahmed Khan, for his unwavering support. I also express my gratitude to our Head of Physics Section, Professor Alim Basa sir, whose leadership has been important. Special thanks to the coordinator of today's lecture, Dr. Priya Hassan Madam, who's played a vital role in organizing and conducting the program. A special acknowledgement to the all faculty members and scholars and the dedicated technical staff and non-teaching staff who played an important role in making this event successful. Lastly, our sincere thanks to the attentive audience whose presence added vibrancy to our discussion. Your lecture and engagement had been this program a resounding success. Thank you so much, all. Shukriya.
Since our speaker is not here, so I request Dr. Priya Hassan to accept our token of appreciation on her behalf. मैं मोहम्मद शहबाज को गुजारिश करती हूँ कि वो यहाँ आए और फूल पेश करें.
So see, Katrien, on your behalf, I get the flowers.
Wonderful. Enjoy them.
Thank you. So we'll do it in front of the camera so that you can see it. Camera, yeah. That's right. Yeah. Okay. Yeah. Thank you. Thanks a lot, Katrien. Thank you. You give the talk, I get the flowers.
Good
Thank
collaboration.
you very much. So thank you very much, and thank you so much. Thank
Thank
you.
you. Yes. Hope to see you. Hope to see you soon. Thank you.
Bye-bye.